section 4-6, page 271. All right, I know it seems bizarre to start a new section right before semester exams. Like I just told you, we've already had our last test and our last quiz, and we don't have any more grades coming in this week, so why are we doing a new section? Well, section 4-6 is graphing with a combination of calculus and calculators. In our section 4-5, when we were doing all of our graphing, we were doing it completely by hand without a calculator, right? But on our exam, you're allowed to use your graphing calculator, right? So it's really frustrating to come back after the exam and me teach you a lesson on how you could have used your calculator to help you do that type of problem on the exam, right? Kind of pointless. So that's the reason we're going to do it now, so that when it comes to the exam, yeah, I do need to use some of the calculus that I was doing in the beginning of this chapter, specifically in 4-5, but I also can use my calculator in conjunction with that. So if I gave you 2x to the 6th plus 3x to the 5th plus 3x cubed minus 2x squared, and I said graph that and give me everything. Give me intervals of increasing, decreasing. Give me maximums and minimums. Give me concave upward and concave downward. Give me points of inflection. All of that different stuff. Whereas before, when I started with this, I would have gone through, the very first thing I would have done is algebraically found the first and the second derivative, right? If I have my calculator laying on my desk, what's the first thing I'm going to do? Throw that into y equals, right? And look at the graph. So totally different approach to how I'm going to do this problem. And that's what they tell me there on 271. It says the method that we used to sketch curves in the preceding section was a culmination of much of our study of differential calculus. The graph was the final object that we produced. In this section, our point of view is completely different, because here we're going to start with the graph produced by the graphing calculator, and then we're going to refine it using calculus. So we could use calculus to make sure that we reveal all the important aspects of the curve, and then with the use of the graphing calculator, we could tackle curves that would be far too complicated to consider without technology. So the idea here is to use them in combination, to not throw out the calculus and go strictly with what the calculator tells me, because we've seen before lies my calculator told me, right? But I also don't want to be doing tedious things by hand that I don't have to if I have my calculator. So I want to see how those two things are related. All right, so for example 1, if I started with 2x to the 6th plus 3x to the 5th plus 3x cubed minus 2x squared, let's throw that into our graphing calculator. So if I go to y equals and I type in that equation, it was 2x to the 6th plus 3x to the 5th plus 3x to the 3rd minus 2x squared. And just by default, I always start with a zoom 6. That's the standard, 10s all the way around. So I would start with a zoom standard. Not really sure exactly what's going on there. I definitely have too many x's over here and too many x's over here. And I'm not seeing enough of my y values. So I need less x's and more y's. Now, there are some people that when they start on their calculator, instead of starting with a zoom 6, their default is to start with zoom fit. I have never taught you to use zoom fit. And the reason for that is it is one of the best ways for your calculator to lead you astray. Because sure enough, if I hit zoom fit on my calculator, this is what it gives me. So I look at that and go, oh, the whole thing is concave upward, and I probably have a relative minimum in there. And that's absolutely wrong. I'm going to have multiple maximums and minimums. I'm going to have multiple intervals of concavity. So it's going to lead me astray. I don't want to do that. So I'm going to need to manually set a window here. So I'm going to need to get rid of some of my x's and then add on some more y's. So what I'm going to use is -3 to 3 for my x's and -20 to 20 for my y's. Now, you could use whatever you want to. That's just what I selected to use. So let's do that. So again, we went into y equals and we put in our equation, that 2x to the 6th equation. and we started with the zoom 6, and that really didn't help us a whole lot. So we said instead, let's go change the window, and let's say that for our x's we want to go from -3 to 3, and for our y's we want to go -20 to 20. That may not cut it. I may actually need to go further than that, but I'll start with that and see where that gets me. All right, now that's looking a little more promising. Okay, so I definitely can see that over here, I'm going to have a relative minimum. I'm not really sure what's going on around 0, though. I'll have to address that in a second. But let's go ahead and let's find the minimum. Now, if I have my calculator, there's a much faster, easier way to find that minimum than to sit here and make a sine graph and all of that good stuff, right? What could I do? What could I do? Second, calculate minimum, right. So I'm going to ask my calculator to find the minimum. It's going to ask me for boundaries because there could be multiple of them. So I'll come over here to the left and enter my left boundary, enter my right boundary and my guess. And it tells me that minimum accurate to 6 decimal places, 5 or 6 decimal places. So that's definitely enough. But I wasn't sure what was going on by 0. So I'm going to need to go back and kind of zoom in a little bit there and see what's going on. So if I'm looking at trying to figure out what's going on right there around 0, pretty much all the action is done between -1 and +1. So I'm going to go back to my window. And this time I'm going to tell it go -1 to +1. 1, not 11. And y is same story. I need to blow that up a little bit and see what's going on. So let's do -1 to +1. And then I'll be able to tell whether I have maximums or minimums or not. All right, so what you think? Do I have anything in there? Yeah, I have a maximum and a minimum, right? And so then I could repeat that same process that we did a second ago, where I could do second trace, which is my calculate menu, and choose number 3 minimum or number 4 maximum as it was appropriate. All right, so just for review, we put the equation into y equals, and we ended up having to set a manual window to get an accurate picture. We could see that we had a relative minimum over here, and so we used the minimum button on our calculator to find that, but we couldn't really tell what was going on over here around 0. So we had to reset our window. So we went through and did -1 to 1 for both the x and the y, and once we did that, it was very clear to see that we were going to have a maximum here and a minimum here. So I could use that calculate button to do that. What would have been another way for me to figure out how many maximums and minimums I had? What? I could find it by hand, yeah, where I'm trying to figure out, if I'm doing it by hand, how am I going to do that? I'm going to do the first derivative test, right? So I'm going to look for where the first derivative changed from positive to negative. Do I have to do that by hand? Is there a way on my calculator to figure out where the derivative changed from positive to negative? So why not combine the calculus with the calculator, right? I could go through and say, what's my first derivative? So you're exactly right. I could use the first derivative test. So what would my first derivative be? Yes, 12x to the 5th plus 15x to the 4th plus 9x squared minus 4x. Now, this was a very easy derivative to calculate, but remember that if it's a complicated derivative, like maybe you're going to have to use chain rule multiple times, or you're going to have a fraction, where you've got to use quotient rule, or a product where you'd have to use product rule, remember, you can get the calculator to do the derivative for you. So you can just tell it, hey, take the derivative of what's in y1 and graph that in y2 for me, and I would still get the same thing as if I took the derivative and typed it into y2 and analyzed it from there. So either way, this one was easy to do, but I could do that. Okay, so if I want to figure out where the derivative changes from positive to negative, I could make a sign graph for the derivative. But to make a sign graph for the derivative, I'm going to have to solve this quintic. Want to do that by hand? No thanks. So as we mentioned, it would be a much better idea to let the calculator graph the derivative for me. If the whole purpose of the sign graph is just to see where the first derivative is positive and negative, then let the calculator graph the first derivative for you so that you can figure out where it's positive and negative, right? So two ways that I could do that. I can go into y equals and literally type that equation in, and I went back to a Zoom standard again. Or you can tell your calculator, hey, take the derivative of what I've got in y1, either one. All right, so what am I looking for here? If I'm looking for relative extrema, what does that look like on this graph of the derivative? Yeah, anywhere the derivative crosses the x-axis. I'm looking for x-intercepts, right? Because the first derivative test for relative extrema says that I'm going to have a relative minimum anywhere the first derivative changes from what to what? Negative to positive, right. So I could look at this graph and say, okay, my first derivative changed from negative to positive. Right there, I should have a minimum there. That's the exact same work that we did a second ago when we identified that minimum, right? But this time, if I want to identify that minimum, because my derivative changed from negative to positive, what button am I going to need to use on my calculator? What? The 0. Yeah, so let's do that. Let's catch up a little bit on our calculator with what we've been doing here in our notes. All right, so I'm going to go to y equals, and I most definitely could type in the first derivative equation. But remember that I can get my calculator to do that for me, particularly if it's a complicated thing. The way that we get this into our calculator is, remember, we go to Math, and we go down to N derivative. So when I choose option number 8 right there, N derivative, it will set it up for me where I can come in down here, and I will need to put in my x value right here. I will either need to retype my equation or just tell it, use what I've already got in y1. And then I will need to come in and tell it to evaluate not just at one particular value for x, but at all values for x. All right, so I'm going to start with a Zoom 6. I may need to change from there, but I'll start with a Zoom 6. And it's going to be very slow in drawing this because it's calculating the derivative at multiple values. Yeah, I can't really tell what's going on precisely there. So maybe I would want to zoom in a little bit to see a little more what's going on. Maybe a Zoom 4. I could always manually set it as well. Okay, now I can see it better. That I can see, okay, we changed from negative to positive at this value. And so you told me that I could find that by using my 0 button. So I'm going to give it a left boundary and a right boundary and a guess. And notice that it gives me that same x value that we had for the x-intercept for the, or for the x value for the relative minimum. Now, it's not giving me the y value. How am I going to find that y value? Plug back in, right. Now, if I've got negative 1.616121, I could, if I wanted to, go back to y equals and turn that first graph back on. I'll turn my second one off, so I'm only working with the original equation. So when I go back to graph that, I can use my value button to plug that value in. So what we had gotten was negative 1.616121 or 22 or something like that. And so it'll find the y value that goes along with that. So that's, again, using our calculus in combination with our calculator to do some of that tedious work for us. All right? And then, of course, I would just repeat that same process for the other two values. So if I wanted a fast, easy way to see how many relative extrema I'm going to have, when I graphed that original function, it was kind of hard to tell how many maximums and minimums there were. I could graph the first derivative and go through and say, okay, sign change right there, sign change right there, sign change right there. That means I'm going to have 3 relative extrema. It changed from negative to positive, so that's going to be a minimum. It changed from positive to negative, that's going to be a maximum. It changed from negative to positive, that's going to be a minimum. And then I could just repeat that process with my 0 button to find the other two the exact same way that we had found that first one. And then I can plug back into my original equation to find the y value that goes along with it. All right. So the second thing that they asked me to do in this problem is to discuss concavity. We've already figured out where my first derivative changed from positive to negative and negative to positive to find relative extrema. I also, from that, if they wanted to know intervals of increasing and decreasing, I could have gotten that because where the first derivative is positive, original function increasing, where the first derivative negative, the original function decreasing. So I could have gotten all of that. But concavity is going to have to come from something different. So if you look at this graph, this was our original graph that we had on our calculator once we reset the window and got a good graph. Can you look at that? I mean, obviously my function is concave upward here and it's concave downward here. Can you see where in here it changes from concave upward to concave downward? No way. I cannot figure that out just by looking at the calculator. I also do not have a handy dandy little point of inflection button on my calculator. I am gonna have to use calculus in conjunction with my calculator. I can't get this just from my calculator alone. All right? So if I want to find my points of inflection, what do I need to know? I need to know the second derivative. What about the second derivative? Possible points of inflection are going to be where the second derivative equals what? 0, yes. So I could go through then and I could find them with my second derivative. Now, if I want to know where my second derivative is equal to 0, here's my second derivative, fairly easy to take by hand. But what I'm left with is a quartic. You want to solve that by hand? It doesn't factor by grouping. So I'd have to do P over Q and all that happy stuff, right? No, thank you. So what could I do instead? All I want to know is where the second derivative is positive and negative and where it has zeros, right? What could I do instead? Yeah, graph the second derivative, look at your x-intercepts. So let's do that. I'm going to throw that second derivative into y3, or I also could just tell my calculator to take the derivative of what's in y2. And when I graph it, I was on a zoom decimal from the last time. That didn't really do me a whole lot of good. So I'm going to need to go back and reset my window. And what we had found earlier when we were working with the original function was that this was a great window to see that original function. So I'm going to try that. It may not be the best fit, but I'm going to try that as my starting point for my second derivative as well. So I'm going to go back to that manual window that we had created. So in y equals, I'm going to turn that original function back off. In y2, we had the derivative of the original function, so that's my first derivative. In y3, then, I'm going to tell it to take the derivative of what's in y2. What was in y2? The first derivative, right. So if I tell it in y3 to take the derivative of what's in y2, then what am I getting? The second derivative, right. I also could have just typed in the second derivative here. No problem at all. We've created that equation. I could just type it in here. All right. But I'm going to ask it to graph that, and I'm going to go back and set the window to what we had said before. Manually, we're going to go -3 to 3 and -20 to 20. And we may have to adjust from there, but that's a good starting point. And again, this is the graph of my second derivative, so it's going to come in really slow as the calculator computes it to graph it. Really slow. All right, so I can see there's a little bit of my graph down here that's going to be missing. But as long as it takes this to graph it, that's not really relevant, right? I don't have to know where the second derivative has a minimum value. I'm really only interested in where the second derivative is positive, negative, and 0, right? And I can see all that, so I'm just going to go with what I've got here. All right, so if they wanted to know intervals of concave upward and concave downward, I could say from -infinity to this point right here, whatever that point happens to end up being, from -infinity to that point, my second derivative is positive, so what is my original function? Concave upward or concave downward? Concave upward, right. And then from this point to this point, my graph is negative, so what does that mean about my original function? Concave upward or concave downward? Concave downward. And then from that point to infinity, my second derivative is positive again, so my original function would have been concave upward. So that would give me my intervals of concavity if I just knew what those two values were. So how do I find those two x-intercepts? Yep, just hit my 0 button. So we're going to go back to second trace, which is my calculate menu, and I'm going to choose my 0 button. And of course I have to give it left bound, right bound guess. And it calculates that value for me. So that would be where my interval changes from concave upward to concave downward. What does that make that? A point of inflection, right. So if I have the x value of the point of inflection, how do I find the y value? Plug it into the original function. So I could go back and turn y1 on if I wanted to. Once I got both of these, I could go back and turn y1 on and use my value button in order to get it to plug those values back in for me to find the y values that go along with them. Okay? And then, of course, I would repeat this process for the other point of inflection over on the other side. So just to review, once we graphed our second derivative, we reset the window and thought about what are we looking for. We're looking for the x-intercepts because those x-intercepts will be my points of inflection where my second derivative is changing sign. And so we use the 0 button to find where the second derivative changed from positive to negative so that we would know where it was changing from concave upward to concave downward and where I would have a point of inflection. And then just a reminder down here of the shortcuts. You can go into y1 and y2 and y3 and literally type your equations. But again, remember that the way we typed this in was in y2, we said take the derivative of what's in y1, that would be the first derivative. And then in y3, take the derivative of what's in y2, that would be my second derivative. So sometimes it's easier just to type the equation in, sometimes it's easier to have your calculator do that for you. Okay? All right. So for our homework tonight, we're just doing a couple of these. 2, 4, and 8, challenge 14.